Okay, last one, part C, region enclosed by the curve. Again, we've got some x's in terms of y, so we have to think sideways. And in my opinion, the easiest way to do this one is to just plot some points, because it's not a real obvious picture. So we'll have our axes first, and then our curves are y equals -2. Oops. And y equals +2. And I'm going to just plug in some points. If I have a +2 and I plug that in, I get a 4 over an 8, so that's a 1/2. So I'm going to put the 1 right here, and I know at 2 I'm going to have a +1/2. Because y is being squared, I know that this is also going to be even around, or I guess I should say symmetric about the x-axis here. And let's plug in 0. We get a 4 over 4, which is a 1. So we got enough information that we can kind of graph the curve now. So there's the region that we're working with. And we're going to cut horizontally because I already have x isolated. So they're going to share a y coordinate. This one has an x coordinate of 0. This one has an x coordinate that comes from the curve, so a 4 over a y squared plus 4, comma, y. So the length of that strip, now here's our sample strip, is going to be 4 over y squared plus 4, and the width is going to be dy. So if I sum all of that up, I'll have the accumulation of that length times the width, and I can go from either -2 to 2, or I can abuse the symmetry of the situation and double the accumulation from 0 to 2. So I think I'm going to do that because I'd rather work with a 0 by hand than with a negative number. So now I have to answer the question, what did I take the derivative of with respect to y that gives me this? And it doesn't look like anything I recognize, but it kind of looks like that arc tangent. So if you recall, we did one pretty similar to this in our section 5.5 when we were doing substitution method. So we're going to have to do a substitution method on this, and before we do substitution, we're going to have to make this look the way it's supposed to. Remember with your arc tangent that we need a y squared or something squared plus a 1, and we've got a 4 there instead. So what we're going to do is we're going to fix that 4 by factoring a 4 out of the bottom. When I factor a 4 out of the bottom, I'll have a y squared over a 4, which is the same as a y over 2 that has been squared, plus 1. These 4's will now cancel, and I'll have a 2 times the integral from 0 to 2 of a 1 over a y over 2 squared plus 1 dy. So we can now see that the thing that has gotten squared is going to be our u, and we'll need to replace both. So let's remember our old integration by substitution backwards, the chain rule. We'll let u equal y over 2. That means dy is going to be du over the derivative of this, which is a half, or a 2 du. So when I replace, I'll have a 2 integral of 1 over u squared plus 1 times a 2 du, and my limits will be y divided, or 0 divided by 2, which is 0, and 2 divided by 2, which is 1. I can pull this constant out in front, and now that inside looks just like the derivative of an arc tangent. So I will rewrite that now as, what did I take the derivative of with respect to u that gave me that? Well, that's the arc tangent of u evaluated from 0 to 1. So I plug in the 1, and I ask myself, what did I take the the tangent of that gave me a 1? And the answer to that is a pi over 4. So I have a 4 times a pi over 4 minus a 4 times, what did I take the tangent of that gave me 0? Well, that's 0. So I end up getting a pi.